Welcome to Maths with EJD. I've been making a series of videos on basic calculus. Previously, I've talked about graphs of functions of real variables and, of course, operations on functions of real variables. Today, I'm going to continue in that on basic calculus, and I'll be talking today about limits and continuity of functions of real variables. And the reason why we're doing all this is because when we talk about calculus, right, differentiation and integration, or what you can call differential calculus and integral calculus, we actually do these things on functions. It can be functions of real variables and functions of complex variables, but our focus here is on functions of real variables. So just like what I did in the previous video, I'm going to I'm going to break this particular module, the second module, into two videos. We'll be talking about limits and continuity of functions of real variables. Of course, under limits, we'll be talking about the definition, the rules of limits, evaluation of limits, and of course, traditionally, you have some exercise to try your hands on. And we'll do the same for continuity of functions. Then we talk about the introduction, the definition, evaluation of continuity, and some exercise to play with. Okay, let's get into it as we focus, first of all, on limits of functions in this video. So, what is the definition of the limits of functions, right? Limits of functions, of course, what you have here is some kind of mathematical definition, but not to worry. When we get into it, you'll find your way. You know how to really take care of all of this. Okay, so let's go. As the independent variable x of a function f of x approaches a given value, the function itself evolves towards a value more concisely. So we have limits of the function f of x as x moves towards a is equal to L, which you can also call f of a, because when you put a into f of x, you get f of a. So as x moves closer to a, as x is approaching a value a, then the function f of x itself is moving closer to L, which is equal to f of a. Now, think about you approaching a wall, right? As you take steps towards the wall, you're getting closer and closer to the wall. But of course, except if you have supernatural powers, you cannot enter the wall. So the wall is like your limit. The wall is like that L, you know. So that's some kind of idea you can think about in a more rigorous way. So I mean, this is a rigorous mathematical definition, especially for people that do it the analytical way. So in a more rigorous way, right, for a particular epsilon, usually in mathematics, when we talk about epsilon or delta, we are talking about positive numbers that are very small, maybe 10 raised power minus 3, which is 0.0001 or something like that, or a number that is very tiny, close to zero, but not zero. So in a more rigorous way, for epsilon less than zero, delta less than zero also, and x approaching a, we say that f of x has a limit L if if the absolute value of f of x minus the limit is less than the epsilon, given that the absolute value of x minus a is less than delta of epsilon. I mean, I know all of that epsilon thing is maybe getting over your head right now, but don't not to worry. I'm going to you are covered because I'll explain all the details when we get into the examples. But for mathematically inclined people, you can get some ideas from here. I think calling epsilon less than zero is actually wrong. That's my mistake. So it should actually be epsilon greater than zero and delta greater than zero. Just like I told you, that those are epsilon and delta are actually very small values. They are very small values. Epsilon greater than zero, delta greater than zero. So they are positive values, but they are very small, very close to zero. Maybe something like 0.001, 0.000001, like 10 raised per minus 3, 10 raised per minus 5, whenever you see epsilon and delta. So it's not less than zero, it should be greater than zero. I apologize for the mistake. Okay, so I mean that's let's get the jargon out of the way. That's some mathematical jargon right there. So let's go on to do to treat the substance of the matter, starting from slide 6. So look at this. Um, Without limits, right? I mean, this is like answering the question of why limits are important. Without limits, calculus is absolutely impossible. So, because as you're going to see when we get to differentiation, you're going to see that calculus is actually based on the idea of limits. And that is why it is important to consider it, first of all, before getting into differentiation and all that. So, as the input into a system is increased or decreased towards a specific value, the output responds accordingly. So it's more like, just like I told you initially, that when you talk about a function, right? It's so you have an input, which is the independent variable, and then it produces an output, which is the dependent variable. So, and that is a very good example of what happens in real life. For instance, as the for instance, as the blood sugar level of an individual tends to towards 6.5% on the AIC test, the person is prone to diabetes. So you see, every almost every human being takes sugar, right? But many people take sugar and they never develop diabetes. So, but the fact is that once you take like diabetes up to a particular level, then you're prone to diabetes, right? And just like you see here, so the test for diabetes is called the A1C test. And then as once your blood level sugar level is approaching 6.5%, then you are, it means that your system, your body is prone to diabetes. So in that case, now we can actually say that your blood sugar level is the independent variable, while diabetes is the dependent variable. So the idea that someone develops diabetes is dependent on their blood sugar level. So blood sugar level is like the input and the output is diabetes. So if your blood sugar level as it is moving towards 6.5%, as a person, the person is moving towards developing diabetes, right? So limits come in handy when we need to find the strength of electric, gravitational, and magnetic fields, as well as the areas, volumes, and weights of objects. So you see the application of limits in all of these things. Like if you see engineering textbook, geology textbook, or even chemistry textbook, sometimes when it gets very advanced, you begin to find limits and all of these things right there. Like you hear something like as time tends towards infinity and things like that, that some things happen to the system. So the idea of limits is very practically useful in our day-to-day activities. So then let's talk about the rules of limits. The rules of limits. What are the rules guiding limits? Because first of all, the limit of a sum or the limit of a difference is the sum or difference of the limits. What that simply means is that if you are going to find the limit of the addition of two functions, you have f of x plus g of x. So as x is approaching a, the limit of their sum is going to approach the sum of their individual limits, meaning that limit of f of x plus g of x is the same thing as limit of f of x as x approaches a plus limit of g of x as x approaches a. That's also true for the difference. So the limit of f of x minus g of x as x approaches a is the same thing as the limit of f of x as x approaches a minus the limit of g of x as x approaches a. So the limit of a sum is the sum of the limits, and the limit of a difference is the sum of is the difference rather of the limits. So that's easy. And the next thing is that the limit of a product is the product of the limits, meaning that if you find the limit of the product of two functions, it is the same thing when you find the limit of each function first before multiplying together. So that is the next rule. The third rule is about quotient. The limit of a quotient is the quotient of the limits. That means if you find the limit of f of x over g of x, it is the same thing as finding the limit of f of x first and then dividing it by the limit of g of x. So the limit of a quotient is the quotient of the limits because quotient is the result of division. Okay. And then you have the fourth one. The limit of a function raised to the power of another function is the limit of the base function raised to the power of the limit of the other function. So the limit of f of x raised to power g of x as x approaches a is the same thing as the limit of f of x as x goes to a raised to power the limit of g of x as x goes to a. So these are very simple and intuitive rules, and then we'll see them practically as we begin to treat problems on this area. Okay, so let's talk about the evaluation of limits. How do you evaluate limits? Okay, the limit of a function only exists if one-sided limits from the positive and negative sides are the same. So now, when we talk about the idea of one-sided limits, right? So if you imagine the number line, on the number line you have 0, right? And to the right you have 1, that's plus 1 for emphasis. You have plus 1, you have plus 2. On the left, you have minus 1. minus 2, and so on and so forth. So if your focus is on, if for instance, around here you have a value called a, right? Now, the two-sided limit is the idea that this number can be approached from the right, and it can be approached from the left. So the approach from the right is your a plus, and the approach from the left is your a minus. Okay? So the limit of a function only exists if one-sided limits from the positive and negative sides are the same. That is, the limit of f of x as x approaches a exists if and only if the limit of f of x as x approaches a from the left is equal to the limit of f of x as x approaches a from the right. So, there are some functions called step functions, for instance. I told you about step functions. Did I talk about step functions when we're talking about functions? I'm not sure, but I think I did. But if not, we're going to encounter that. For step functions can have different values defined within different limits, right? So if for any function, whether step or not, the limit, if you find the limit as as x approaches the limit from the negative side, and then x approaches the limit from the uh, approaches the limit from the positive side, and the value towards which they tend is not the same, then you cannot say that the limit exists. So you will get this better when I explain, when we take example of a step function along the line. Okay, so generally, a rule of thumb for evaluating limit is to first substitute the value the dependent variable approaches into the given function. If that fails, other techniques can be considered. So the first thing you do when you see a limit is to substitute the value that x is approaching into the function you are given. So if that fails, then you can now think of other things, and we are going to see all that. Okay. Okay, let's look at this very first example. So you have to find the limit of x squared plus 5x minus 2 divided by 3x plus 2 as x approaches 2. This is a rational function because this is a polynomial divided by another polynomial, and that is why it is a rational function. So as x is approaching 2. So from the rule of thumb I just told you about, the first thing you should do when you see a limit question is to substitute directly the value that x is approaching. So if after substituting that, you do not get a good answer. Now, a good answer for limit is anything apart from infinity. So if you get infinity, that's a bad answer. If you get 0, that's okay. If you get anything, if you get -5, that's okay. If you get minus anything, it's okay. The only time you have a bad answer is when your limit evaluates to infinity. So once you get infinity, don't give up that the solution does not exist. So it means you can try other techniques which you are going to be exposed to in the course of this class. Okay, so you have the limit of x squared plus 5x minus 2 divided by 3x plus 2 as x approaches 0. So first thing, substitute the value of 2. That's the first thing you should do. So x squared means you have 2 squared. 5x means you have 5 times 2 minus 2 divided by 3x plus 2. That's 3 times 2 plus 2. So 2 squared is 4. 5 times 2 is 10. That's 14 minus 2. That gives you 12. Then 3 times 2 is 6 plus 2, 8. So you have 12 over 8, which evaluates to 3 over 2. So that simply means that as x is approaching 2, then this expression is approaching 3 over 2. Mind you, it doesn't mean that x is 2, right? It means that x is moving towards 2. So as x is moving towards 2, the function itself is moving towards 3 over 2. The function is not at 3 over 2. It is moving towards it. It's just like that blood sugar thing. As blood sugar is approaching 6.5%, then the body is approaching diabetes. Not like it's there. So the closer you get to that value, the closer the function also gets to its own limit. Okay, so this is a very good example. Now you see that the limit of this thing is actually 3 over 2. So let's see, as x is approaching 2, right? X is approaching 2. So I have plotted the graph of this rational function here, and look at 2 here. This is 2 on the value of x, right? And then look at the function it corresponds with. Look at the function. This is the function it corresponds with. So we don't worry about this -2. So we are talking about this 2 now. So what we are saying is that as x is moving towards 2, either from the right or from the left. So what does the function tell you? Let me remove this. Okay, so this is 2 right here. So as x is approaching 2 from the left and from the right, what does this function move towards? So the function is moving towards, so that's along this line. So as x is moving towards 2, it comes somewhere around here, 2. Then also from here, it comes to the same point. So if you trace this on this place, you'll discover that this is like, the answer we got was 3 over 2, right? 3 over 2 is the same thing as 1.5. So that's 1.5. So you can see this is 4 divisions from 0 to 2. So that's 2 divided by 4. Okay. 2 divided by 4 is 0.5. Basically, that's what I mean. So this is 0.5. This is 0.5. This is 1.0. This is 1.5. So you see that as x is approaching 2, so as x is approaching 2 this way, best of all, along the line, this is where the function is coming. And of course, from the other side, it results to the same. So if you trace that to the y-axis, you get 1.5, which is 3 over 2 that we got in the previous calculation. So you can also read, it means you can read off limits even from graphs. That's what this one has told you. So sometimes to find limits, you can plot the graph of the function and focus on the number towards which it is tending. For instance, if you are taking the limit as x, the limit of the same function as x approaches -2. So look at this -2 now. So it means this is going towards this place and it stops somewhere around here. It's coming this way and stops around here. So if you trace it down, you discover that the limit is 2. So for this same function now, so if you take limit as x tends to -2 for the same function, you discover that it's actually evaluated to 2. So you can find limits by plotting the graphs of the function. Okay, so let's go to slide 11. Slide 11 to see another example. Okay, now see this. Now you see the first evaluation we did, we got a good answer, which is 3 over 2. 3 over 2. Now here, let's see this. Evaluate limit as x squared minus 5x plus 6 over x squared minus 4. I mean, evaluate the limit of x squared minus 5 over 6, 5x plus 6 divided by x squared minus 4 as x approaches 2. Okay, so what's the first thing you do? Like I told you, substitute x into the expression, I mean, the value of x, which the value towards which x is tending, put it into the function directly. So that means for x squared, you have 2 squared minus 5x, you have 5 times 2 plus 6. Then x squared again, you have 2 squared minus 4. And then if you evaluate that, what do you get? This is 2 raised to the power of 2, that is 4. This is 10. 4 minus 10 is minus 6 plus 6, that's 0. 2 squared is 4. 4 minus 4 again, 0. And anything divided by 0 is infinity. Now, this is not infinity because of this 0. It is actually because of this 0. So whenever you are dividing by 0, you are going to get infinity. And like I told you, infinity is a bad answer. 0 is even a good answer, but infinity is a bad answer. And when do you get infinity? Either when you are looking for, you are dividing by 0, or you get the square root of a negative number. As far as limit is concerned, you can say it's undefined. So when we substitute directly, the limit is indeterminate. So when you get infinity, you say that the limit is indeterminate. So we have to look for other ways out. So we have to check other ways out. Now, if you do the graphical method like I did the other time, see what's happening here. So we are saying that x is approaching 2, right? X is approaching 2. So when x approaches 2, this is 10, right? This is 1, 2. So this is 2, 4, 6, 8, 10. So this is your 2 right here. This is 2. X is approaching 2. Yeah, x approaches 2. Yes, I was going to be sure if it's -2 or 2. So this is what 2 looks like here. So it means if you trace, so it means yeah, the limit is somewhere around this place. So, and that's looking like 0 or so, or a very tiny number for that matter. Okay, so but definitely it's not undefined, because if it was to be undefined, it means that the graph will not even cross that line. So because the graph is crossing that particular x equals 2, because the graph doesn't jump at this point, then it means that the limit exists, and it's I mean, it is some very tiny value, maybe something like 0 point something. So we'll see that as we use other techniques. Yeah, it's -1.1 over 4, that's minus 0.25. Okay, but then how do we get that? So you have substituted directly and you got infinity. So you can now check the function, and from the graph, you have seen that the function does exist. I mean, the limit of that function exists. So one technique you can use is to factorize. So you have x squared minus 5x plus 6, right? You need to factorize that. How do you factorize this? This is what basically you do. You have minus 5 and 6, right? So you look for two numbers that you will multiply. When you multiply the two numbers, you have to get positive 6. But when you add or subtract, when you add or subtract, you get 5. And those two numbers, the same two numbers, you multiply to get 6, but when you add, you get 5. And those, they are usually factors of 6. So the two factors of 6 we know will be 2 and 3 that can give you anything close to 5. And since this is minus 5, right? And this is plus 6. So it has to be, it can be plus plus. If it is plus plus, plus 2 times plus 3 is 6, but it is not minus 5. But then it can be minus 2 times minus 3. Minus 2 times minus 3 will give you minus 6. And then minus 2 minus 5, let me do it elsewhere. And then minus 2 minus 3 will give you minus 5. So you have met this condition. Two numbers to add or subtract, and you get minus 5. The same two numbers you multiply, you get 6. And those numbers are minus 3 and minus 2. So you can now say, okay, this is x squared minus 5 is the same thing as minus 2x minus 3x, which you got, plus 6. So, and that is, you can factorize. X is common, so you have x into x minus 2 minus 3 into, minus 3 is outside, right? So x remains inside. Minus divided by plus is minus. 3 and 6, that is 2. So that's why you have x minus 2 into x minus, x minus 3 into x minus 2, or either way, x minus 2, x minus 3. That's why you have x minus 2, x minus 3. And then for x squared, right? X squared minus 4. You should have heard about difference of two squares. A squared minus b squared is the same thing as a minus b into a plus b. So because if you expand this, you're going to get a squared minus b squared. So you see that now x squared minus 5x plus 6 is the same thing as x minus 2, x minus 3, and the base, the denominator, is difference of two squares. So you have x minus 2x plus 2. So from that, you can see x minus 2 cancels, x minus 2 simply cancels x minus 2. And then you are left with the limit of x minus 3 over x plus 2. So after you have simplified like this, you can now put 2. So you have 2 minus 3 over 2 plus 2. 2 minus 3 is minus 1, 2 plus 2 is 4. And that is why the limit of that expression, which was infinity when you substitute directly, is actually minus 1 over 4. So don't give up if after you've substituted directly and you get infinity. Fine, the answer may actually be infinity, but before you conclude, you have to try other means. And one of the means to try is to factorize. And from factorization, you can simplify the expression, and then you still end up substituting the 2 like you did here. And then now we know the limit is minus 1 over 4, which is minus 0.25, which is, from that graph, you discover that it's, if you look at the graph again, so the value here, okay, I've gone way too far. Let me just erase this so you can see that. Yeah, so you see, because the graph is too close, so you may not be able to see distinctly that what you have there is actually at x equals 2 here, it's actually minus 0.25. That's the limit as x approaches 2. This is 2 now, as x approaches 2 from the left and the right. All right, so that's one thing. So another method you can use for that kind of expression is what is called the L'Hopital's rule. The L'Hopital's rule simply says that if you have a function like a rational function, right? Okay, I mean, it's right here. The L'Hopital's rule states that the limit as x approaches a of f of x over g of x is the same thing as when prime, we are still going to differentiate and integrate, but then it's like we are getting ahead of ourselves because L'Hopital can help us out with the limit, right? So the first thing, you have f of x, g of x. So L'Hopital is saying that the limit is still the same if you differentiate f of x on its own first, and you differentiate g of x on its own. That's why we have f prime of x over g prime of x. So if you differentiate first and you now put the value towards which x is tending, it's still the same limit. That's what L'Hopital says. And of course, even if at this stage it is still undefined, you can keep differentiating till you get to a point where you can actually evaluate the limit. So N here talks about higher derivatives. So if you do the first derivative and it is still undefined, do the second, do the third, and keep going until you get an answer. All right. Of course, you may end up still getting infinity, but make sure you exhaust all the options first of all. So if you want to use L'Hopital's rule for this, right? Of course, I've not taught you differentiation per se, but I'm just going to do like a crash course before we get into the main thing. So we have limit as x approaches to of x squared minus 5x plus 6 over x squared minus 4. So limit as x approaches to now. So you differentiate x squared minus 5x plus 6, and you have x squared minus 4. And of course, the simple rule for differentiation is generally, if you have a x raised to power n, if this is y, right, then dy dx, when we get there fully, you'll understand. Dy dx is a times the power of x, which is n, times x itself raised to power n minus 1. So once you multiply by n down here, then you reduce the power there by 1. So let me remove this to make it clear. Yeah, so you have a x raised to power n minus 1. So that means if you have x raised to power 2, a here is 1. So 2 times 1 is 2. Then you have x power 2 before, so it becomes power 1. Minus, 5x is like 5x raised to power 1. So 1 times 5. So this is, if you differentiate this, you have 5 times 1, that's 5. X raised to power 1 minus 1, 0. And anything raised to power 0 is 1. That's why this ends up being 5. And if you differentiate 6, 6 is like 6x raised to power 0, because x raised to power 0 is 1. 6 times 1 is 6. So if you differentiate this, you have 0 times 6, x raised to power 0 minus 1, which is automatically gone, because this 0 will just cancel everything out. So that's why when you differentiate a constant, it goes to 0. So it doesn't it doesn't exist anymore. So you see that here, you have, if you differentiate 5x squared minus 5x plus 6, you get 2x minus 5. And then if you differentiate now for L'Hopital's rule, you differentiate the top and the bottom separately. It's not like quotient rule, because you're still going to get to quotient rule. So you differentiate this separately, you differentiate this separately. If you differentiate this separately, this is x raised power 2 is like 1 x raised power 2. 1 times 2 is 2. The power of x reduces to 1. And this is constant. So if you differentiate for that, it's like 4x raised power 0. So 0 times 4, 0 times whatever else, that's 0. So once you've differentiated this way, you can now put you keep putting the limit until you substitute it. So once you substitute it, you have 2 into 2 minus 5 over 2 into 2. So 2 times 2, 4 minus 5, that is minus 1. Then 2 times 2 is 4. So you still end up getting your minus 1 over 4. So whether you factorize or you use L'Hopital's rule, you still get the same results as expected. All right. So that is that. So we go for another example. This is evaluate limit of sine x over x as x approaches 0. How do you do this? First thing, like I told you, rule of the thumb, substitute directly whatever x is approaching. So that means you have sine 0 over 0. Of course, sine 0 is 0. And then x, at x, when x is 0, this is also 0. So the answer is still undefined. So, but then don't give up. The answer may actually be undefined, but you don't know until you try all the other methods. So since direct substitution results to infinity, we have to explore other methods. So, and let's see that exploration in slide 16. Okay, of course, one of the explorations you can do is graphical method, right? So imagine x is approaching 0, and this is x equals 0 on the graph. So as x is moving towards this value, from the right and from the left, so it means it's going to come to somewhere around here. Now, let me remove the line to make it clearer. So the point is coming here. So, and you can see that point is like 1, right? So this is 0, this is 1. Okay, sorry, if this is 2, right? This is 0 0.5, this is 1, this is 1.5, this is 2. So it means as x is approaching 0 from the right and the left, the expression sine x over x is approaching 1. So, this graph now is the graph of sine x over x. So it means the limit actually exists, though when you substitute directly, you cannot find it. The answer is undefined. So now let's think of methods we can use for this. Again, I just told you about L'Hopital's rule. So in fact, L'Hopital's rule is one of the easiest ways to find this kind of limits. Other methods can be quite tasking, you know. So L'Hopital's rule again for this, you have limit as x goes to 0 of sine x over x. So L'Hopital says if you differentiate the top and bottom separately, I mean the numerator and denominator separately, and you divide and you evaluate the limit, it is still okay. So here we said d dx of sine x, that's what you differentiate sine x and then you differentiate x separately. So again here you have limit as x goes to 0 of differentiate sine x, you get cos x, differentiate x, you get 1. We are still going to talk about how you differentiate sine x to get cos x and things like that. And then here you have cos x over 1. That means you have limits as x goes to 0 of cos x. So you can now substitute 0. So if you put 0 into cos x, you have cos 0. And cos 0 is 1 if you punch your calculator. When along the line, I'll teach trigonometry, and then you're going to see that cos 0. So there are some special angles like angle 0 degrees, angle 30 degrees, angle 45 degrees, angle 60 degrees, and an angle 90 degrees. So those angles, you should know them offhand, or if you don't know them offhand, you should be able to derive them. I'll be explaining all that when I ever get to teach trig. Okay, so that's L'Hopital's rule, and we see, according to what the graph says, the limit of sine x over x as x goes to 0 is 1. And we have got that from L'Hopital's rule. Let's see another method called the Taylor's expansion. The Taylor's expansion. So the Taylor's expansion is that, I told you about, when we're talking about functions, right? I talked about transcendental functions. And I said they are functions that cannot be expressed as polynomials, right? So, thankfully, Taylor's expansion can help you to express any kind of function you have, whether transcendental or not, as a polynomial, at least an approximation. You can approximate whatever function, whether trig or inverse trig or anything, as an approximate polynomial function using Taylor's expansion. And this is what the Taylor's expansion is. It's like. I mean, if you want to see it as a formula, that is it. So the Taylor's expansion of a given function f of x is given as this. So it means put 0 into the original function, then next differentiate the function and put 0 and then multiply by x, plus differentiate the second time, put 0, divide by 2 factorial, and multiply by x squared, then differentiate the third time, divide by 3 factorial, multiply by x cubed, and so on and so forth. So you keep doing this to the degree of accuracy you actually want, okay? So if that is the case now, our f of x here is actually sine x. If we want to evaluate the limit of sine x over x as x approaches 0. So if you can do this for sine x, let's see what we get. So for sine x, we have, first of all, you need f of 0. So it means you have to differentiate. I mean, you need to put 0 directly into that. So f of x is sine x. So f of 0 will just be sine 0, which is 0 taken. Then you differentiate sine x and you get cos x. So that's f prime of x is cos x. So f prime of 0 means cos 0, and that is 1. Okay, so it means that you're going to have 1 coming here. Here, this one is already 0. Then f prime prime of 0. So that is f prime prime of x. You have minus, so differentiate cos x, you have minus sine x. Evaluate that at 0. You now get minus sine 0. And sine 0 is 0, so the minus doesn't help anything. Then, so it means that this second derivative here is 0. Then you go again, the third one, differentiate minus sine x. Differentiate sine x, you get cos x, so there's minus there. So that's the third derivative. Put 0, you get minus cos 0, which is minus 1. So this guy is going to be minus 1. Don't forget, so it means this is going to be 1 times x, 0, 1 times x, 0x squared, minus x cubed, and so on and so forth. So this is the fourth derivative, right? Differentiate cos x, you get minus sine x. There was a minus there before, so it becomes sine x. Then evaluate that at 0. So that means sine 0, and that is still 0. So the fourth derivative is also 0. So you see that for odd derivatives, right? Is it odd now? I mean, for even derivatives, you get 0, but for odd derivatives, you get 1. And probably that's why we say that sine x is an odd function. And then the fifth derivative now, differentiate sine x, you get cos x. So for the fifth derivative, you also get cos 0, which is 1. So at the end of the day, we can put all this together to get this nice expression that sine x is 0 plus, that 1 times x plus 0 minus, minus x cubed over 3 factorial plus 0 plus x raised to power 5 over 5 factorial. Everything at the end of the day for sine x is x minus x cubed over 3 factorial plus x5 over 5 factorial. Okay, so now that we have expressed it this way, so we can now go back and do the limit and say limit as x goes to 0 of sine x over x is equal to limit as x goes to 0 of, so sine x now is x minus x cubed over 3 factorial plus x5 over 5 factorial divided by x. Okay, so and we can do this division very well. We can say x divided by x minus x cubed divided by x all over 3 factorial plus x raised to power 5 divided by x all over 5 factorial. Just divide each thing by x because everything is being divided by x. So x over x is 1. X cubed divided by x is x squared over 3 factorial. This is x over 5 factorial. And then, here you still have limit as x tends to 0. So you cannot put the 0. So there's no 0 with this one. So you have 1 minus, this is 0 squared. This is actually 0 squared, not 0 cubed. So this is 0 squared divided by 5 factorial. This is 0 raised to power 4 over 5 factorial. So all this will just go to 0, and you have 1. And that tallies with the graph, and it tallies with what we got from L'Hopital's rule. So it means that limit sine x over x actually has a limit as x approaches 0 by whatever. So you can use L'Hopital, and you can use this Taylor's expansion for sine x. Okay. I hope it's coming well. So let's go on to, so sometimes also you want to evaluate a limit as x approaches infinity. So evaluate a limit as x approaches infinity. So this is another thing entirely. So like I told you, the rule of the thumb, substitute directly whatever x is approaching. So here you want to evaluate 3x squared plus 5x minus 1 over 7x squared plus 3 as x goes to infinity. So put infinity. So you have put infinity for x. That's 3 infinity squared plus 5 infinity minus 1 all over 7 infinity squared plus 3. So, and once infinity is added to anything or subtracted from anything, and anything is subtracted from it, it is squared, everything ends up being infinity over infinity, and that's infinity. So since the result is indeterminate, we need to find other means of solution. In this case, we divide each term by the x with the highest degree, which is x squared. So, whenever you have this kind of thing, and of course it's evaluated to infinity, so look for the highest x, and it is x squared in this case. So divide each term by that x squared and see what you get at the end of the day. So let's see that. Let's see that in the next slide. And this is it here, right here. So you have limits of 3x squared plus 5x minus 1 over 7x squared plus 3. So like I said you should divide each term by x squared. So that's 3x squared over x squared minus plus 5x over x squared minus 1 over x squared all over 7x squared over x squared plus 3 over x squared. So at the end of the day, you divide through. So x squared cancels x squared cancels x squared. X cancels one of these. So you have 5 over, so you have 3 here, 5 over x, and this is 1 over x squared. Then here you have 7 left, and this is 3 over x squared. So at this point now, you can put infinity, right? You can put infinity. So if you put infinity, so everywhere you see, you still have x left, put infinity. So that means you have 3 plus 5 over infinity minus 1 over infinity squared plus 7 plus all over 7 plus 3 over infinity squared. So, and that's 3 plus 5 over infinity minus infinity squared is infinity. Then plus, all over 7 plus infinity squared again is infinity. So anywhere you have infinity left. Now, how do we even get this? You know that we already said it before that when you divide anything, let's say you have x divided by 0, it gives you infinity. So anything divided by 0 gives you infinity. So can you just put this over 1 and try to cross multiply? So it means that you have x times 1, which is x, equals 0 times infinity. So can you divide through by infinity? So you have x divided by infinity equals 0 infinity divided by infinity. So you see infinity cancels infinity, so that anything divided by infinity is equal to 0. So that means anything divided by 0 is infinity, and anything divided by infinity is 0. So at the end of the day, anything divided by infinity just goes to 0. So you have 3 over 7, and this is it. So it means that though initially when you substituted infinity, the answer was undefined. But when you divide through by the highest power of x, you can end up getting a limit for that expression. So don't be in a hurry to give up. Try. So whenever x is tending towards infinity, you divide by the highest power of x, whether in the numerator or denominator. And you see graphically, right? The answer we got there is 3 over 7. That's like 0.4 something. So, and that's what you can see here as x is approaching infinity. So x is approaching infinity. That means x is going all the way down, all the way down. So you see that this graph is stabilizing at some point here, and it's like some very tiny value, which tallies with 3 over 7, which is 0.4 something. And you see the same thing on the left-hand side. So as x approaches infinity, whether to the positive infinity or negative infinity, you see the function is stabilizing around 3 over 7, right? Okay, so let's take another example close to that. We have 3x squared plus 5x minus 1 divided by 7x plus 3. So again, of course, you already know that if you divide, once there's x here and there's all x up there, you just know that everything is going to result to infinity. So you divide through by the highest power of x, and the highest power of x anyway is x squared. So do it up. You have 3x squared over x squared plus 5x over x squared minus 1 over x squared. Then go down 7x over x squared plus 3 over x squared. And simplify, x squared cancels out. This cancels 1. This cancels 1. So you have 3 plus 5 over x minus 1 over x squared all over 7 over x plus 3 over x squared. Now in this case, the x doesn't finish down here, but let's see what happens. So here you have 3 plus 5 over infinity minus 1 over infinity squared all over 7 over infinity plus 3 over infinity squared. So you see that the infinities are still remaining down here. So it means you're going to have 3 plus 0 minus 0 all over 0 plus 0. So that's 3 over 0, which is infinity. So you see that because if the power up there is x squared and the one down is x, so the infinity, I mean the x's don't cancel out. And that ends up, so in this case now you can actually conclude that the answer is infinity because there's nothing else you can do. The answer is actually infinity in this particular case. So, and you see, when you plot this graph now, as x is approaching infinity, the positive infinity, and as it is approaching the negative infinity, there's no, I mean, all the graph is just going, it's just diverging, it's going all the way there. It's nothing, so you're not getting a particular answer. So that's why the limit of this kind of expression does not exist. So you can see all the two graphs, they are just moving away. So let's look at something like this now. The first case we looked at where the power at the top and the power at the bottom are the same. And the second case we looked at where the power at the top is higher than the power down. So this third example, we have the power up is less than the power down. Let's see what happens in this case. So you have evaluate limit as x tends to infinity of 5x minus 1 over 7x squared plus 3. So again, you already know as far as there is x and there is x, and once you put infinity, everything is going to be infinity, and that is not what you need. So the next thing, divide by the highest x, which is x squared. So divide by x squared all the way. So you have one x canceling one here. All this x will cancel all this, and you have all the other. So you have 5 over x minus 1 over x squared divided by 7 plus 3 over x squared. So anywhere there is x, everything goes to 0. So this is 0, this is 0, and then you have 7 plus 3 over infinity. So 0, 0, 0. So you have 0 minus 0 over 7 plus 0. And 0 over 7 is 0. Now, like I told you, 0 is a good answer, 0 is not like infinity. So the only bad answer is infinity when it comes to limit. So 0 is a good answer. So the limit of this function is actually 0, okay? So let's see the graph of that in slide 26, I guess. Yeah, slide 26. Now you can see this, that as x approaches infinity on the positive side and x approaches infinity on the negative side, you see that the graph now is coming back to 0 down here. And you see that this one is rising and it's stabilizing at 0. So that's why the limit of this one is actually 0. Okay. So we have a summary for all these things that just happened now. So that's like some tips on limits as x tends to infinity. So given a rational function f of x equals p over x all over q over p of x all over q of x, of course q of x must not be equal to 0. We saw this before in the previous one of the previous videos about rational function, the ratio of two polynomials. Now, so if the degree of p of x, that's the numerator, is greater than the degree of q of x, the limit is undefined. So like you can see, if the degree of p of x of the numerator rather is greater than the degree of the numerator. Degree means the highest power of x. So the highest power of x here is 2 of the numerator, and of the denominator is 1. So in this case, you should know that the answer is going to be undefined. But then if the degree of p of x is equal to the degree of q of x, the limit is the ratio of the coefficients of the highest terms in x for p of x and q of x respectively. So that's why if you're doing multi-choice questions like objective, you don't have to waste your time. So once you are told that x is tending towards infinity, just look at it that, oh, okay. So once these ones have the same power, just cancel it out and you have 3 over 7 straight. Don't even worry yourself. But here, when you come and see that the power at the top is bigger than the power down, when you cancel by x squared, x will still be remaining down. So it means at the end of the day, you'll be dividing by 0. That'll be undefined. But then in the third case, if the degree of p of x is less than the degree of q of x, that is the degree of the numerator is less than the degree of the denominator, the limit will be 0. So for instance here, if you divide through by x squared, x will finish from here, but it will not finish here. So it means you're going to have 0 over something. That here you're just going to have 0/7, and the answer will be 0, which is also a good answer. So those are some tips on limits as x approaches infinity. So with that, we come to the end of limits of functions of real variables. So here you have some questions to try your hands on. Evaluate the following. Number one, limit of e raised power x minus 1 divided by x. Of course, you already know, substitute directly and try. Then again, this is limit of e raised power x multiplied by ln of 2x plus 3. Then you have limit 1 minus cos x over x. You have limit of 2x raised power sine x as x approaches pi over 2. And you have this, and you have all that. Try your hands on them and see how well you understand all I've been saying. Thank you so much for listening. See you in the next video where I talk about continuity of functions of real variables. If you have not subscribed to this channel, please feel free to subscribe and press the notification button so you can always get notified when I upload a new video. Thank you.